right, so let's talk about mixtures and solutions. So we're going to be looking at what these are and also things like solubility. So how you can look at what rate things are dissolving, things like that. So first, let's look at what it means to be a mixture versus what it means to be a solution. So pure substances can only contain one type of element or compound. So we talked in previous videos about elements. So elements, again, those are things that are made up of just one atom. And then compounds are anything that are made up of a combination of elements, but the compound for a pure substance has to be all the same compound. So for example, for a pure substance of like water, for it to be pure water, it can only contain water. It can't contain anything else. It can't contain ions, or like you can see here, this is definitely not a pure substance because first you can tell it's coffee, so it doesn't have just water molecules in it. It definitely has other things like caffeine and so forth. But also this individual is taking sugar. Sugar would be a pure substance because it's the compound of sugar or sucrose. So you can see here, C12H22O11. So that is the compound. So this would be the compound, but by putting it into water, this is now no longer a pure substance. So the sugar would no longer be a pure substance because it's been mixed into, in this case, a cup of coffee. So a mixture is a collection of two or more pure substances. So it can be elements or compounds. Usually when we're looking at mixtures, we're looking at compounds. But for example, an alloy where you've got multiple metals, that would be considered a mixture because you've got multiple elements that have been mixed together, but they aren't bound together as a compound. Mixtures can be separated by physical means. So they're not bound together. Again, they're not in some sort of bond, so they don't have a ionic bond or a covalent bond. You can even pull apart alloys. It's more complicated, but you can pull apart alloys. Metallic bonds aren't permanent. The metallic bond still holds the metallic elements together, but an alloy is still a mixture because you've got those different metals intermingled together. And these mixtures can be homogeneous or heterogeneous. So homo for same, so they are going to be, in this case, made of the same sort of states. So that's what we're looking at here. So homogeneous for the same state. And that basically you can't differentiate between the different elements or compounds when you observe the mixture. Versus heterogeneous. Heterogeneous, you can actually observe the different pieces of that mixture. So they can either be easily observed pieces, even though they're in the same state, or they're in separate states, and therefore easy to differentiate different parts of that mixture. So we're going to take a look at what this means with some examples. So here we've got some different types of matter. So you can see we've got granite and snow in a snow globe, pizza, seawater, clear seawater, white gold, and air. And so the question is, which of these is a heterogeneous mixture and which is a homogeneous mixture? Because they are all mixtures. So again, the way you tell them apart, homogeneous mixtures, when you look at them, they are the same, meaning that you cannot tell the elements or the compounds apart from each other in the mixture, versus heterogeneous, where you can tell the pieces and parts apart from each other in the mixture. And you may have, as you've been looking at this, been able to figure out that everything in the top row are the heterogeneous mixtures. So we've got granite. This is made up of different types of minerals. That's what gives you the different colors, the speckling. Snow in the snow globe, so you've got two different states in this case, solid for the snow, liquid for the water that's in the snow globe. And then the pizza, you've got all the different toppings and the crusts, so this is definitely a heterogeneous mixture. Versus the homogeneous ones that are down on the bottom, these you cannot see the different components of the mixtures. So for example, the air is going to be made up of a lot of different gases. The water is going to be made up of, yes, water, but it's going to have different salts and minerals dissolved in it, which we cannot observe. And then white gold, I mentioned in a previous video, this is made up of gold and palladium. It's an alloy. And so it's not easy for us to be able to see those two materials because they've been mixed together. So let's look more closely at these homogeneous mixtures because there are actually two groups of homogeneous mixtures. So heterogeneous, they're just heterogeneous. So you can see and observe the different pieces and parts in them. Boom, done. Homogeneous mixtures, these guys, little bit different because there are two types. So there's a suspension, and this is where you have different components in different phases. So this does appear, possibly depending on how it's mixed, sometimes to look like a heterogeneous mixture, but it is a homogeneous mixture if it is done correctly, if you want to think of it that way. So what am I talking about here? So a suspension is where you have generally something like two different things like a liquid and a solid that are mixed together. So those are the two different phases, liquid and solid, mixed together so that they are basically, it's difficult to distinguish them from each other. So what would be an example of this? Examples of suspensions would be things like milk, blood, and the clouds. So clouds would be an example of liquid and gas as far as a suspension goes. These are difficult to look at and see the different phases because they are so well mixed together. I mean, think about, for example, milk. It looks like a solid white liquid, but it does have different components in different phases. So a majority of milk is actually liquid, water, but there are the proteins and fats and so forth that are the solids in milk. They're just really well mixed in. If you think about looking at the carton, it's homogenized. That gives you kind of an idea of why it's a homogeneous mixture or suspension. They've been well mixed in. You can separate those proteins and fats out so that you can get the solid and then the liquid. In fact, that's what they do with whole milk to make things like cheese. Blood, same thing. So the red blood cells and platelets and white blood cells, those are the solid components. Again, we can separate them out. They're really well mixed in, hence the suspension. The pieces are hanging in the liquid, but you can spin in a centrifuge that blood and get the solid parts to sink to the bottom. How can you tell it's a suspension versus our other one that we're going to talk about, which is a solution? Shine a light at it. If you shine a light in it and you can see kind of pieces, or kind of, it gets that, if you think about like a light beam through the air and you see the dust, that's another suspension. So if you shine a light in it and you can see those particles, then that's a suspension. Versus a solution, if you shine a light through a solution, it's going to appear clear. because the components are all in the same phase. That means that they have dissolved into each other. They've all moved into that same phase. So you cannot distinguish them at all in a solution. So let's talk about solutions. So solutions are where all the components are in the same phase. So think about something like salt water, seawater. So you've got water, which in seawater is what we call the solvent. So the solvent is the major component. It's what everything is basically dissolved in. And so for seawater, water would be the solvent. And then you've got solutes. Solutes are the minor component, or components, the things that are dissolved in it. And so for seawater, that would be things like the salts, the minerals, and so forth that are dissolved into the seawater, which you can get back, right? In a solution, you can get those back, just like in any mixture, you can get the materials back through physical means. So like in a heterogeneous mixture, it's easy, right? You can just pick and pull the pieces apart. Suspensions, you can do things like I was talking about, like doing centrifuging and so forth to get the solid parts to sink out. In a solution, usually what you need to do is do something like heating or something like that to basically remove the solvent. So if you wanted to get the salt from salt water, you would heat or evaporate the water in some way. In fact, sorry, I wanted to show you this. I actually done this kind of by accident. So if you look at this cup, I'm hoping you can see there are giant salt crystals down in the bottom of this cup. This was actually filled with a salt solution, and I forgot about it, and the water evaporated, and over time the salt got left behind, the solute, and the water left, the solute got left behind. That would be the physical means for separating the parts of the solution, so you can get those pieces and parts back. Now, with a solution, we can have different types of a solution in the sense of how much solute is there. And so that's what these pictures down here are showing you. So in this case, they're making sugar water. So the solute is sucrose, and the solvent is water. And they have 3 different types of solution here. So first we've got an unsaturated solution. So we're talking about saturated versus unsaturated. So you can see along the bottom, all 3 of these beakers have the same amount of water. So they all have 100 milliliters of water at the same temperature. What's different is the amount of sugar that has been added. So the first beaker has just 150 grams of sugar, sucrose, that's been added to the beaker. And this is what we would consider an unsaturated solution compared to beaker B. So beaker B has 200 grams of sucrose, and this is considered a saturated solution versus beaker A because this has more in it than the other one. Okay, so that's what we're talking about, saturated versus unsaturated. So a saturated solution is going to contain more of the solute. And in this case, this is actually pretty close to the saturation point as far as the maximum saturation, the maximum amount of solute. And the reason why we know that is because what happens in beaker C. Beaker C is also saturated compared to beaker A. And it is probably pretty equal, but probably a little more saturated than beaker B. We've got 250 grams of sucrose that they attempted to dissolve in there. But they're saying that 50 grams of sucrose, so yeah, it's actually the same saturation as beaker B, sorry. So they're saying 50 grams of sucrose is sitting undissolved on the bottom of the beaker. So in this case, for this amount of water, 200 grams of sucrose is the maximum amount that can go into the solvent. So this is at maximum saturation. Can't get any more of the solute to go in. Now, could we actually get more of this sugar to dissolve? And I'm guessing you're probably thinking yes. And the easiest way to do it, and you may know this if you've done it before, is to heat it. You can actually increase the saturation, the amount of solute you can dissolve, by increasing the heat most of the time. We'll talk about why that doesn't always work here in a second. But you can increase the heat. That will increase the amount of solute that can go into the solution, and then this would be creating a super saturated solution. So if you put in more than the maximum, the saturated solution, if you put in more than what can normally be held, you get a super saturated solution. And that super saturated solution, if you disturb it by, for example, putting a string in it, it will start to pull the solute out. And this is how you make something like rock candy, if you've ever made rock candy before. All right. So here what I've got is just kind of an overview of these different things that I've been talking about so far. So over here, some examples of pure materials. So we've got things like elements and compounds. So if they are completely by themselves, they would be considered pure. Impure or mixtures are any time where you have more than one element or compound mixed together. Some examples of heterogeneous mixtures that are not the same as what we saw before. So these are probably pretty straightforward. And then examples of solutions that we've been talking about. I didn't mention this one, but air is a solution because they're in the same phase and we can separate them out, but it takes some time and energy. And then suspensions, most of these we talked about when I talked about suspensions. All right, the last thing to talk about with mixtures and solutions is solubility. So solubility is just the ability of a solute to dissolve a solvent. In a solvent. That doesn't make any sense. So how well can a solute dissolve is what we're talking about. And so the thing is that not all solvents can dissolve all solutes. And the thing is that a solute is said to have an appreciable solubility. If it has an appreciable solubility, it's said to be soluble. So, for example, we know that in water, salt and sugar are definitely soluble because we know that they'll dissolve. We also know that oxygen can dissolve in water because that's how things like fish and so forth breathe. However, other things are not so great at dissolving into water. So, for example, things like nail polish and oil are not soluble in water. They don't dissolve into water, and so they are not soluble in water, but they are soluble in other materials. And so the solubility all depends on what the solvent is. And so that's what we have to keep in mind, that the solubility is dependent on the solvent. So is everything soluble in water? Now, I've already talked about that a little bit. You can't dissolve everything in water, which is a good thing. We don't want everything to be able to dissolve in water. And the thing is that temperature does have an effect on solubility. So when I was talking previously about saturating solutions like sugar solutions, you can increase the temperature and that will increase the solubility of salt, or of sugar. It'll also increase the solubility of salt. So you can get more of those two solutes, those two materials. You can increase that solubility by increasing temperature. But that's not the case for all materials. So if we take a look here, the increase in temperature will increase solubility of salt just a little bit, but compared to the solubility of sugar, which isn't on here, the solubility of sugar will go up a lot as you increase the temperature versus the solubility of salt. That's why you can't dissolve a lot of water, or a lot of salt into water. But you can see these other salts, for example, potassium chloride has a little bit more solubility as you increase the temperature, but lithium chloride and sodium nitrate, the solubility increases a lot as you increase the temperature. So you can dissolve a lot more of those materials into water. But that doesn't work for everything. There are materials that as you increase the temperature, the solubility goes down. And so that is a problem depending on what you're trying to do. And that's something to keep in mind, that temperature is something to make sure you know if you're trying to dissolve a material. For example, if you're trying to dissolve, paint or any sort of other resin, things like that, you need to make sure that you know what the solubility is of it in its solvent, whatever that might be, and if temperature has an effect. Because even, you can see here with sodium nitrate, small changes in temperature have a huge difference on solubility, and that may be a problem depending on what you're trying to do with it. And then just a fun fact about solubility, because you have experienced this, I'm sure. So what we've got here are 2 bottles of soda, and one bottle has actually not had its top opened yet, and the other one has. And so you can see the difference in the carbon dioxide gas. So the carbon dioxide molecules, when the top is on, they actually are going to be forced back into the liquid. So temperature and pressure can both make an effect on the solubility of the material. But most of them, you can see, are up above the water, or of the cola level in this case. But they're bouncing around, and so they will, under pressure, continue to stay in the liquid. But when you release that pressure, there aren't those molecules up at top anymore. The lid's off, and this is why you get the bubbling, because carbon dioxide doesn't easily stay soluble in water. And so once you release the pressure, that gas becomes less soluble and releases out into the atmosphere. You may realize at this point that temperature does have an effect on the solubility of carbon dioxide, because you are going to get a bigger whoosh of, that hiss or pop when you open a soda that's warm versus a soda that's cold. And that is because carbon dioxide is actually going to be more soluble in cold than it is in warm. So if you keep your soda cold, the carbon is going to stay in the soda longer than if you have that soda warm. The warmer it is, the more active the gas is, and the less soluble it becomes, and it will come out of the soda. All right, that's the end of mixtures and solubility.